Thank you very much, Scott. I assume you're hearing me right now. Okay, thank you. So today, hello everyone. Today we'll be talking about how the OPERA project is advancing continental scale ground motion monitoring across North America with a focus on our surface displacement product or DISP. So our goal here is basically to really bridge the gap between this massive volume of SAR data and making that information usable for your science and decision making. I'm co-presenting with Sara. Hand over the presentation to her later about the algorithm of the displacement product. So just, a brief overview. So this work actually represents a large collaboration across JPL, NASA centers, USGS, universities, and our partner organizations. It's really a team effort to basically operationalize remote sensing products at scale. So about OPERA. OPERA stands for Observational Products for End Users from Remote Sensing Analysis. It is designed to go beyond single missions and instead integrate multiple satellite systems like Sentinel-1, Harmonized Landsat, and Sentinel-2 products, and of course, NISAR. OPERA is a project funded by InSAR, or NASA's Satellite Needs Working Group. And it's currently led by JPL again across this collaboration with many institutes. Our emphasis is delivering ready-to-use cloud-based or cloud-optimized GIS-friendly products. So again, you don't have to deal with complex radar processing, for example, for data for the displacement products. We want to break the processing barrier so that you can focus on the analysis and decision making rather than data processing. Within OPERA, we have this stakeholder engagement program. We actively engage with stakeholders, partners, and end users through workshops and this kind of platforms, webinars, tutorials, and of course, one-on-one support. This ensures that our products are not only scientifically robust, but actually they can be adapted and useful in many of your workflows. So we maintain a regularly updated website and manage an active stakeholder SEP program to engage with science and application again. And we support our broader SNWG efforts. So for the next few slides, we will walk you through the main components of the OPERA displacement products, an overview of the products that we have with focus on this. Then, of course, the algorithm that Sara will talk about later, and then the product validation that we have made to ensure the accuracy of our displacement product, and finally showcase some examples and how you can start using the displacement data. Okay, so this slide shows the broader OPERA product ecosystem. We span from level 2 input products like the RTC, which is like the radiometric terrain corrected products, and CSLC, core-registered single-loop complex product. They are level 2 products. They serve as input to our higher level products, which include, for example, our water product, the DSWX, or we call it DSWX, which gives you a measurement of like surface water extent or maps from optical, and as well as our input products. Coverage spans near global. It's already available now. You can access them from Earth Data Search or PODAC. We also have disturbance products or DISP, which maps disturbances using, again, optical and SAR imagery. They are also available now from the NASA DAX or Earth Data Search. They also are near global in terms of coverage. And finally, which is the focus of this presentation, is the surface displacement, which gives you this measurement of the displacement in the line of sight. And the input products come from both Sentinel-1 and soon NISAR. However, the coverage of this product is within North America, and that simply means all U.S. Mainland U.S. And U.S. territories, parts of Canada within the 200 kilometers from the U.S. border, and all those mainland countries from southern U.S. border up to and including Panama. We have level 4 products that will come soon and will be available. For example, in 2028, the vertical land motion, the VLM will be derived from the displacement products. You will have a surface displacement map in the vertical and horizontal where possible from Sentinel-1 and again NISAR datasets. Coverage is North America, similar to the displacement. We have a Tropo product within the produced by the OPERA project. This is a global estimate of atmospheric delay that can help correct atmospheric signal from any SAR mission. It's sensor agnostic. It's provided in a zenith measurement. So you can just translate it to whatever satellite geometry you are using to correct for Tropo. Most of our products, or all of our products except for VLM, are in 30-meter spatial resolution. And the Tropo correction is in 8 kilometers. Temporal sampling would be sub-weekly to weekly. And again, all our products are freely available through our SNWG data portal and on NASA Earth Data. Can just search for those words, and then you can get access to those data sets. So the OPERA displacement is again the focus of this presentation. There is a revisit interval of 6 to 24 days, 6 to over 24 days. The product record for Sentinel-1 begins July 2016, and we are processing until 2029. The product record for NISAR is still a TBD, but right now I think it's June 2026, which is the calibrated start of the calibrated version of the NISAR products. You can access all these products through ASF DAC. The displacement S1 are now available. You can see, for example, this is the velocity map over North America. This is a visualization made possible through the displacement portal hosted at ASF. The displacement product is, again, the first ever operational surface displacement time series available for North America. It is also the first InSAR product certified CEOS analysis ready data. If you're curious what CEOS-ARD means, it's basically already processed products that are already processed to a level where users can immediately analyze without the heavy pre-processing, which is critical for your time series applications, and of course, interoperability of these data sets. With regard to the displacement product, when you download one of the displacement product, it is distributed as an NC or NetCDF file with this kind of file format here. You will have 14, when you load it, you will see 14 layers. The main layer is the displacement layer. It's the primary data layer. And we have this short wavelength layer, which I would discuss further later on. This is the layer that we use to display in ASF DAC. We also provide the correction layers, such as the ionosphere delay, solid or tight, perpendicular baseline, to help with the time series. We provide quality metrics and to assess the consistency and reliability of the pixels within each frame, and also water mass. So now I will just hand it over to Sara here. She will discuss or walk us through the algorithm that drives the displacement products for both Sentinel-1 and NISAR.
Thanks,
Sara.
Grace. Yep. Thank you. Yeah, my name is Sara Mirzaee. I will briefly talk about the DISP algorithm that we're using in OPERA. It's based on this paper that you're seeing that is currently almost accepted under review. And please go next slide. Yeah, so similar to OPERA project, there was European Ground Motion Service that is producing displacement maps over Europe, and you're all familiar with. There are some differences between these two products. EGMS is with Sentinel-1 data from February 2015 to December 2023, and it's updating annually. For OPERA, the scope is to produce displacement with Sentinel-1 and NISAR data. For Sentinel-1, the archive is using July 2016 up to right now it's December 2025, and it's ongoing. And the plan is to dynamically update for each acquisition that is coming. So the challenge is turning this vast amount of data into timely, actionable information. About the conventional techniques that were commonly used for especially distributed scatters processing in time series analysis, we are all familiar with the SPAS. SPAS uses a set of interferograms over time that are multi-looked, and creates a network with small spatial and temporal baselines, and then inverts it to get the displacement time series. Can you go to the next slide? Yeah, but we have found, or there are a lot of papers currently published now, that there are biases in this time series from using only a SPAS algorithm, which comes from the multi-looking and using limited number of interferograms. If you look at this figure, which was published by Ansari in 2021, if you use 5 nearest neighbor interferograms, you get the left map, and then when you increase the number of interferograms, like the middle one, you get a different map, and then when you use all pairs of interferograms, you get that one on the right. So this workflow could be expensive, because if you want to use all the interferograms possible, it's not really operationally friendly. So an efficient way to estimate this time series from all possible pairs is to use the full covariance matrix. This was also published by several authors, first in 2007 and 2008 by Tabaldinian et al. It's called the covariance-based approach. So on the left, you can see a matrix, covariance matrix. Each element of this matrix represents an interferogram, and a multi-looked interferogram. But that multi-looking is now, in this technique, adaptively performing on each pixel. So in order to create this covariance matrix, you need the vector of complex SLCs at each pixel. So dxi is a vector of complex SLCs at pixel x at time I. And if you multiply it by the Hermitian conjugate operation, and then sum it over a neighborhood, which we assume that neighborhood, all the pixels are statistically homogeneous, then you get this covariance matrix. There are a couple of algorithms to estimate the phase series from this matrix. It's maximum likelihood estimator, phase triangulation algorithm known as a CEOS-ARD, which was published in 2011. And then there are eigenvalue decomposition techniques. So what we use for OPERA is the last one, the combined EMI and EVD. And what is essentially it is doing is to look at this covariance matrix and perform EMI, which was published by InSAR in 2018. In this algorithm, there is a step to invert this matrix. And for that, it has to be positive semi-definite. But if it's not invertible, so our technique is to switch back to EVD. So for each pixel, we evaluate this and then perform either EMI or EVD if it's not invertible. The considerations is that we are performing this inversion for like over a large stack of SLCs, and that could be computationally expensive, regardless of which one of those estimators we use. And every time a new acquisition becomes available, so for those techniques, it was like you have to do this inversion again to get the time series connected. But this made approaches available or think of ideas to provide sequential estimators, firstly introduced by InSAR in 2017. And the way it works is that it divides the whole stack of SLCs into batches, which we call mini stacks. And then for each mini stack, which is like through time, if you for example, say the first 15 images in time, you perform the phase linking, and then the output would be a phase series for those 15 images. And then with PCA algorithm, you kind of squeeze those first few images into one synthetic image called compressed SLC, and then use that in the next mini stack. Yes, so in this way, you are creating the interforograms between the second mini stack and also kind of with the first mini stack through that one compressed SLC, and you preserve those interforograms. Yeah, so for this, after you perform the phase linking for the second one, you also get a compressed SLC, and this goes on adding each compressed SLC to the next mini stack. We have an example here for just showing a comparison between different processing techniques. On the top left, you see the spas results over Mud Creek landslide. On the right, you see the output using full covariance matrix that I just described. And lower left, there is an image using the PS analysis. So these are only PS pixels. And yeah, you can see that if you want a better coverage, maybe the full covariance in full resolution would be an optimal choice. There are limitations for phase linking. So for OPERA, we have a 72 hours latency requirement. And if you want to go ahead with this sequential estimator, you have to wait for each mini stack to accumulate. And it's like if you want, for example, 15 images to accumulate, it's like 6 months of data, and you have to wait for that to accumulate. For that, we have proposed an incremental phase linking technique. If you go to the next slide. Yes. So we don't wait. With each acquisition that is coming, we perform, we create a mini stack with that acquisition. And for example, if we have processed the first mini stack until from 0 to M acquisitions, we have a compressed SLC next time, there's one more acquisition coming. So it's from the acquisition 1 to n+1. So kind of we move this mini stack forward in time. And when it reaches to the, to a full mini stack, we create that compressed SLC and move forward again. This is how the incremental phase linking works. And with this, we can eliminate that long latency and do this process. We don't need to reprocess the entire archive. Please, yeah. The second limitation is that with sequential estimator, that was proposed by InSAR, there is a step called datum adjustment because each mini stack is referenced to the first image of that mini stack, and it has a separate datum. So after all of them are processed, you have to do kind of an adjustment to connect them and build the time series. And that is also time consuming, and you need to have access to previous data. For this one, we have a strategy to revise the referencing. Please go to the next. Yeah. So in this figure, I'm showing just an illustration for showing each mini stack, how the reference moves forward. So for the first mini stack in figure A, imagine we have 4 SLCs, and then the output would be a phase series relative to the first image. And we have a compressed SLC in that. For the second mini stack in B, you have the compressed SLC colored in blue and images 5 to 8. And the output would be referenced to that compressed SLC instead of the first image of that mini stack. This way, the referencing moves forward, and all the mini stacks are connected, and you don't need to do this datum adjustment anymore. Please go next. Yeah, so overall, just showing the flowchart of what we are doing in OPERA for displacement. The middle box shows the algorithm. It's the first step is to find PS and DS. I will show in a little bit how the PSs are selected, but after you find statistical homogeneous pixels for DSs, you create that covariance matrix, or we call it coherence matrix, and we perform the phase linking. After phase linking, you can unwrap any sort of network from that because the closure phase is already removed. So you can unwrap any order of interferograms. We select nearest 3 interferograms, and then we do some pre-processing, unwrap them, and then invert for time series. So I want to mention a little bit difference between Sentinel-1 and NISAR here. On the left, you can see the inputs to this algorithm. Sentinel-1 has the CSLC, NISAR GSLC, and beside that, the other inputs that we have are the compressed SLCs from previous mini stacks. And then we have the auxiliary data, DEM, water mask, geometry, and we have the ionosphere auxiliary files. For Sentinel-1, we use the tech maps, and for NISAR, we use the GunW products. Those contain a ionosphere phase screen layer, which is obtained from split spectrum technique. And the output is almost similar. They all output displacement and a compressed SLC for each mini stack. Please go to the next. Yes, for PS, we have a simple way to just use this amplitude dispersion from Fretin 2000. And it's because it's simple, and also you can move it forward in time. So with each mini stack, we store this amplitude mean, and we can we can kind of update it through time. So it's like PSs are updated for each mini stack every time. So if a PS is changed because of construction or anything, this will be updated each time. Next. We also mentioned that the posting of the displacement products are 30 meter, but CSLCs are 5 by 10 from Sentinel-1 and 5 by 5 for NISAR. So how do we get to the 30 meter posting? It's by decimation. If we assume that on the left we have the window size in which we look at the pixels for decimation, if it's all DS in this window, we perform that full covariance estimation and we output one pixel. If there are one PS in this window, we output the PS value. And if we have multiple PS, we output the strongest PS based on the amplitude dispersion. Next. Yeah, here just showing different correction layers and how they impact the products. For Sentinel-1, we do not correct anything. We just provide those correction layers in the displacement products, and they are ionosphere corrections, solid tides, and the perpendicular baselines in which could be used for DM correction. But ionosphere corrections are calculated based on tech values, as I just mentioned in the previous slides. For troposphere corrections, you have to download them from ASF portal as the Zenith radar delays. I think Grace showed that earlier. And please go back. Yeah, just to mention that the first row are the displacement without any correction that we provide. And then if you correct for tropo, that is like the major contribution here. And and solid tides are very minor, as you can see in the third and fourth row. Versus if you look at the NISAR data, the first row is displacement without any correction, and the second row is after ionospheric correction. And you see that has a huge impact on NISAR because of the frequency. So for NISAR data, we are correcting for ionosphere based on the GunW products. And that is the difference between these two products. Yeah, and with that, I just will hand the floor again to Grace. Thank you.
Thank you so much, Sarah. That was great. Yeah, so for this slide and forward, I will discuss the product validation and like showcase some applications of the displacement products. So this is specific for the Sentinel-1 because we are yet to release the NISAR products next year. So just a context of like the validation. Validation is an independent quantitative assessment to ensure that the products that we produce meets defined standards for accuracy, quality, and reliability, which are directly tied to the project science objectives during the formulation and conceptualization period. For displacement, the key requirement is to achieve about 5 millimeters per year of accuracy or better over spatial scales between 100 meters to 50 kilometers from 4 years of regularly sampled Sentinel-1 data sets, at least 80% of the acquisition at 12-day sampling or better in regions where the interferometric signal is maintained. We use VB polarization in IW mode to evaluate our products. In general, so our validation relies in the use of independent ground-based data sets like GNSS, and of course, complementary data or remote sensing data sets to confirm product accuracy. I'll mention this two validation techniques after this slide. So given the large spatial scale of displacement, Sentinel-1 over North America, our strategy ensures that we pick frames that are representative across these diverse terrain, surface conditions, and environmental settings. We selected validation sites across both stable and deforming regions, including areas affected by tectonics, subsidence, volcanic activity, again, spanning different land cover types and terrain. So we have two validation approach. The first one is the direct comparison of GNSS and the InSAR time series or velocity over regions with dense GNSS networks. This is an example frame in California, frame 11.11.5. What we did is basically we computed for the velocities for the displacement products from 2016. Again, during the time we were doing this was, I think, 2024. So we have 8 years of product record. We computed the InSAR velocity, and then we compared it with the GNSS velocity. We did a double difference approach. As you can see, for example, in here, bin the results, and then if it's lower than 5 millimeters, we're marking the frame as pass. If it's above that 5 millimeter per year threshold or product accuracy that we set, we're marking it as failed. For the validation approach 2, we're computing for InSAR residual analysis. We're taking random pairs of pixels within the frame where we don't have significantly deforming regions. So we mask these areas, for example, in this frame here. We bind it again, and then we give a pass or fail mark if it's below 5 millimeters per year. These are sample plots comparing the displacement Sentinel-1 and GNSS time series. This is for a frame in Sacramento, California. You can see in red points here are the GNSS daily positions. The blue points are the displacement Sentinel-1 positions from OPERA over a given station. This one is the Dixon. We reference it to this reference point SACR. You can see here, this is the difference between the red and the blue points in this plot below. And these are the correlation plots between displacement, and on the x-axis is GNSS. You can see how good the correlation is for these 3 sample plots here. And even here, I'm very impressed with how it could recover even the seasonal signal in this region. For just a summary of our validation results, before we released it, we passed 100% of the validation data for VA1 approach. That is directly comparing GPS with our displacement product. And then for the VA2 approach, which is InSAR residual analysis, we passed 91% of the validation data that we evaluated. Now I'm gonna walk you through some applications of the displacement Sentinel-1 product. This is for landslides. This example is showing a Pacific Coast highway along Big Sur, California, which is home to dozens of active slow-moving landslides. This is a slide from Dr. Alexander Handwerger, our deputy project scientist. Here, the displacement product from OPERA captures the ground motion caused by the landslides. You can see this cumulative displacement animation. These data sets can be used to better understand landslide mechanics and improve information, of course, for our decision makers in infrastructure monitoring aspect. In this plot here, for example, this is plotting several pixels within this region, and the blue curve here or line is the precipitation time series from 2017, I suppose, to just around 2025, and the red line are the minimum pixel values, and then orange is the median. You can see that around 2017 and parts of, I believe, 2023, and then here, this was a period of accelerated deformation that can be linked to heavy precipitation during the rainy season. Another example where you can use the displacement product is for monitoring land subsidence. This image here, this is from the Arizona water resource. Is this showing San Simon or the Bowie subsidence area in Arizona? This here on the left side is our OPERA surface displacement time series, showing the same subsidence over this agricultural region. And here is the time series related to that. So if you are in this monitoring water resource and land use, it's very helpful to not deal anymore with the processing of the complex SAR data and just be able to get this displacement time series and immediately apply it to or use it for your decision making. There are plenty more examples that could capture that can be captured by the displacement product, including volcanic unrest, earthquakes, and here is like anthropogenic deformation related to wastewater injection in Texas. Here, for example, this images above is showing that there was a time around 2018 that Mount Edgecombe in Alaska was reawakened. So you can see that it ramped up some kind of inflation activities here. This one here, again, is showing the Ridgecrest earthquake that occurred in July 2019. You can see a very nice strike slip faulting deformation captured by the displacement product. We run a working group prior to the release of the displacement products. They were early adopters of the products, and they provide us feedback on the quality and science application of our displacement product. And we received several great feedbacks about the use of it. This is analysis shared by Danny Lindsay from UC Berkeley back then. She was comparing creep rate measurements along Hayward Fault. This is, I guess, from the ground measurements, and this is the velocity map derived from Sentinel-1. So I've shown you plenty of examples, and I'm pretty sure by now you're curious on how you can get started on this OPERA products. Fortunately, we've made the access straightforward for you. Again, just to remove those complex processing barriers for the researchers and practitioners here. What you can do, for example, is you may just want to go to displacement.asf.alaska.edu. This is our displacement portal. It's hosted in ASF. If you click on that, you will see something like this. There's a disclaimer that we put for the use of this of the portal for your decision making or analysis. Here, what we are showing, as I've mentioned earlier, is the short wavelength product. Its main intention is for visualization. It uses this some kind of filtering window, removing long wavelengths more than 25 kilometers. And this could filter, for example, signals like atmospheric noise, and would result to highlighting local signals such as landslides. But it can also introduce some artifacts, for example, in Central Valley, where you have this large spatial scale of subsidence. So we encourage that you read our FAQ before interpreting our data using the displacement portal. If you really want to dive more into the analysis, you can extract the nominal displacement layer, download the actual product from ASM Vertex or Earth Data. Just an overview of what to expect for the displacement portal. Here you have the ascending coverage of the displacement product. And here is just what we have for descending coverage. The gap is, of course, related to acquisition plan of Sentinel-1. So if you want to do your own in-depth analysis, we have Python-based notebooks that you could leverage. Here, for example, this one is even running in Google Colab. What we were showing here is subsidence in Arizona and how you reconstruct the displacement time series, connect the mini stacks, for example, and recover this kind of plots. So you can follow our GitHub repo, download the notebooks, try it out, and if you encounter any issues, feel free to reach out to the team. So just to summarize the entire presentation, we're coming to the end of it. I hope we have made our case that OPERA transforms these large volumes of remote sensing product, in particular in this case, SAR data, into ready-to-use displacement time series. Our displacement products provides time series in Continental-Scale. This is the first operational time series for North America, offering sub-weekly to weekly temporal sampling. It's the first ever certified product by CEOS-ARD. We use incremental phase linking to update our time series, and this can result to just within hours of new satellite products generated within few hours of newly acquired data sets without reprocessing the entire historical archive. Our products meet the project requirements with certainty levels of 5 millimeters per year or better, and we validated our products against GNSS networks and, of course, through InSAR residual analysis. Finally, and most importantly, we support a wide range of applications from hazards to infrastructure monitoring to regional or large-scale tectonics monitoring. You can see, again, those applications that I've just shown you a while ago. For more information and data access tutorials, we have this links available here if you want to go back to this presentation and explore more on how you could use the the displacement products. We offer one-on-one technical guidance and expert consultation for product support, especially if you are a stakeholder working in the federal or state agency. So please feel free to contact us. And with that, thank you very much for your attention. Sara and I are now happy to take questions. Thank you.
All right, thank you. That was great. We do have a bunch of questions in already. I'll just remind you, if you think of more, put them in the Q&A box, and we'll see how many we can work through here. We have about 13 minutes, so we should be able to get to some. There are a lot of technical questions in here. Maybe I'll ask one higher level question from a position of less knowledge first. Not to make you pick a favorite, but what do you think is the biggest advantage of all this work that you've done on this product for the data users? If you run into someone and try to tell them, they're doing research and you have this data for them, where do you start? What is the biggest selling point for them?
I'll start because I think so during my grad school, I would spend, I don't know, months of just preparing the data just to be able to retrieve the displacement time series. Now it's going to be provided to you through an accessible portal to just get it and do, for example, I'm a volcano geodesist. I would just take the products and do immediate kind of first order modeling of what is the source of the deformation. And, months, I would say that, during back then when I was doing my grad school, again, it would take the first year to just do the product pre-processing and arrive into this kind of really science grade time series that now you can use for deeper analysis. Sara, what's your experience on it?
Yeah, me as well. So just processing all these products is really time consuming and it requires resources, but it's already available through this project. So it's really great to have, like the research based on that.
I always tell our project scientists, I wish that this is already available during the time I was doing my PhD, so I don't need to bother about this. But yeah, we're making it more, I guess easier for everyone to now just focus on the science.
Love that. All right, well, I'll get into the submitted questions now. So this first question is about the tropospheric products, and there are kind of several questions about it, so I can repeat part of this as needed. But so what's the spatial resolution of the tropo products? What are the inputs? Have they been validated in mountainous regions? Could you use them for like InSAR small scale signals like landslides, for example?
Oh, Grace, do you want to talk about it?
The resolution is 8 kilometers. It's a zenith delay measurement. What are the other points about the small scale
been
deformation?
validated in mountainous regions?
So we did not validate the actual products, but I believe we have. So there's a paper that will be coming soon, I hope, about this. But we have quantified the uncertainty of the global products.
Okay.
But there is no validation that we did like what we did for the displacement product. Sara, would you like to add on the small scale deformation signals? Application of tropo.
Yeah.
Well, small scale, usually the referencing removes these signals, so it depends on how small or how big is your area.
And then the tropo is based on actual weather data.
Gotcha. Okay, the next question, forgive me if I misunderstand this, but if there is a gap in IFG network over a certain area, how is that handled?
Yeah, so we usually have gaps, especially for snow, because I think there's another question related to snow. I'm answering that too. If you have seasonal like a snow-covered interferograms, you have to remove them because even though you find you can make that covariance matrix and it will recover the coherence, but the scatters are essentially different. One of them is from the ground, one of them is from the snow, so it decorrelates. So we came to the conclusion to remove those pairs. But also there are gaps because of the decommissioning of, for example, Sentinel-1B. And for some of the frames, we saw that there are like 3 years of gaps. And in that situation, we came to the decision to make it separate. So we stop at the end of at the beginning of the gap and then restart the displacement after the data is coming again.
Okay. Next question, what is the best way to evaluate an inverted displacement time series from the OPERA product? Does it come with an uncertainty estimate or layer?
Yes, we have a couple of layers in the displacement. So for the time series, we have the time series residuals. We have the kind of uncertain, the Kramer lower bound calculated. and also similarity index. These things could help for finding the good pixels and estimating the uncertainty. Essentially, mostly is the time series residuals.
Okay. Could you please explain where we should apply the solid Earth tides correction using the Sentinel-1 data?
Yeah, so solid Earth tides are really small. It's up to 30 to 40 centimeter. And it's for the large scale when you have like a big track and you want to remove that ramp from it. But for small scale processing, it doesn't really have much effect when you reference to a station in that small region. It will be the same for all the pixels. So it's not really effective for small regions.
Let's try. So for pixel selection, what about temporary PS? Do you see a decrease in PS density as the stack gets longer? Are you considering or planning to consider appearing and disappearing PSs?
Yeah, as I mentioned, like PS estimation is for each mini stack, and for each mini stack we provide a PS mask, so you can see that it will be updated for each time you process. If the mini stack size is 15, every 15 acquisition, that can be updated based on appearing or disappearing then.
Great. This is very efficient. These are great questions, and we're getting through them too. The GNSS values from the stations, are they corrected for ionospheric and tropospheric delays and other instrument changes that happen over time?
No, we did not correct for those corrections, nor we apply it on the displacement product. So they are evaluated accordingly.
What's the reliability of the Sentinel-1 C-band displacement product over vegetated areas? Is the signal simply masked out, or does it still provide usable information to some extent?
It depends on the vegetation, how dense it is. If it's bare, we have reliable pixels over those regions because phase linking is to improve distributed scatterers. But for dense vegetation, yeah, we cannot do anything. That's the inherent characteristic of the Sentinel-1C data, and you have to mask them out.
All right, next up. The only way that I've found to download OPERA data is either single point time series or displacement products which cover large areas. Is there currently an API or planned feature that allows subsetting a displacement product or downloading time series for like a custom polygon area?
So our Python-based tools can do that. The Opera utils, in fact, which you can install under that notebook that I have presented earlier, that can be used to just crop on your bounding box, so you don't have to download this, netcdf files, because each file can be like 400 megabytes. It's really heavy, and if you're just looking at this small area of deformation, you don't need to download the 200 by 240 kilometer frame, right? So we have those tools for you.
Okay, hopefully a simple one here. Is OPERA the official NISAR distribution of level 3 or level 4 data?
So for the short answer, I don't think we are the official NISAR distributor. We are producing displacement time series for over North America to complement the Sentinel-1 displacement time series that we have right now. For NISAR related products and higher level of products, it's a separate kind of collection, I would say, but they can still be downloaded on the same distributed archive system, which is ASF.
Okay, I think we can get through a couple more still, which will be almost everyone. If I want to get a VLM product using Sentinel data for a particular location outside North America, Could I use the Opera Python notebooks to do it? And if so, might JPL be able to help with advice?
So the Opera Python notebooks are currently intended to run using Opera displacement products. Basically, you already have the displacement products on the DAC and you just pull them and then you recreate the time series, wrap it, whatever manipulation you want to do with it, filter it. But if you want to do it outside the North America geographic scope, you have to run the code yourself, the Dolphin code, for example, which is open source. And then convert it to VLM. Sorry, I forgot the VLM part. Yeah.
Sure. One that might be, maybe we make sure we were clear about an earlier question. Aren't the GNSS position estimates from independent data centers or the group at JPL so generally corrected for ionospheric, tropospheric delays during the processing, like before you use it?
We use the UNR data products for it. And again, I guess for Sentinel-1, that we don't apply any tropo corrections on the displacement time series.
So using them as available, right? I think we can squeeze one more in. So roll the dice. How are the displacement products filtered? Is it temporal coherence? We might have touched on this a little bit, but.
So there's a water mask as well as a similarity index, and we provide a recommended mask for each product you can use for filtering pixels.